right. So, hi, welcome. Oh my God, my voice is really loud. Okay, I hope it works for you. Thank you so much for coming to this session. I just got the go-ahead from our technician over here saying that it's time to start. So welcome to the session called Principles for Designing and Deploying Scalable Applications on Kubernetes. Okay, so what's the goal of this talk? Well, I'm here to give you actionable advice. How to get the most out of your Kubernetes platform, how to express clearly what it is you want it to do so that it can support your applications. And yeah, hi, welcome. By making the right choice when you design and you deploy your applications, you gain all the benefits of Kubernetes. You know, automation, security, availability, all the benefits that made you go for Kubernetes in the first place, but maybe you don't feel like you're getting quite just yet. Well, that's what I'm here for, to give you the tools that you wanted. Who am I? Well, my name is Lars. Hi. I've been working with the cloud since before it was actually called the cloud, and I've been programming since the days of QBasic, not quite as long as the Sinclair guy, maybe, that was just in this room. I've studied how it all works. I've been, what happens when the illusion of infinite resources breaks down. And now you can either hire me as a consultant or any of my other colleagues at Elastisys, or connect with me on LinkedIn to learn about the latest in security, DevOps, Kubernetes, and also compassionate leadership, because that's something that I care a lot about. I'm not here to make like a sales pitch for Elastisys. I'm just wearing the t-shirt, obviously. But come talk to me afterwards if you want to find out how we can help companies use Kubernetes on GDPR-friendly alternatives to the major US cloud providers. Now, okay, so this is not the first time that I've given this talk for you. This has taught me at least two things. Thing number one, some of these principles are going to be, well, less difficult, some more difficult to actually implement and practice. Now, the impact will also differ. Previous audiences, they've asked for guidance like this that I show on screen right now. So like, how difficult is this to do in real life, and what's the impact? So basically, if you see something and you hear me talk about something and you think, wow, that sounds really smart, and then you look at the difficulty score and go like, okay, then you at least you know that going in, right? We heard this morning in the keynote that it's not always so easy to estimate how long something will take. I'm not saying that this is a perfect estimate. Obviously, there are companies out there that also want to help you make estimates better. But yeah, it's at least an attempt from my side. I do this with companies, so hopefully my guess is rather good. Okay, so there's one more thing that I need you to know. Yes, it's loading. And that is that this talk is a mix of beginner and advanced topics. So it's fine if you feel like some of the things that I say are maybe far beyond your current usage level of Kubernetes. Now that's the whole point, right? This is a very diverse crowd, and I want everyone to feel like they learned something. So feedback that I've gotten is that no matter where you are on your Kubernetes journey, people have found this talk informative. So far, I've never had anyone say that they didn't at least learn something new. And I see that as a very positive thing, and I don't know, maybe today is the day. Maybe today somebody will raise their hand afterwards and go like, this was a waste of my time. And if so, hypothetical person, I'm sorry. Hopefully there won't be too many of you. If you feel like even most of this presentation is too advanced, don't worry. You get the slides afterwards somehow, and you can refer back to them. All right, and then maybe you can go like, oh, well, that thing that I heard about at Øredev, now I actually have time to implement it, or now I can actually do it. All right, so point being, I hope you all learned something today. So let's begin, and I promise it's going to be with something easy. All right, now this is deceptively easy, okay, but still. So, Kubernetes. Does everybody know what Kubernetes is? I mean, you went to a talk about Kubernetes. Hands up. Yes, yes, let's do some exercise in the afternoon. Hands up if you know what Kubernetes is. Okay, I'm going to pretend I didn't see anyone not raising their hand. Okay, Kubernetes is a thing that figures out, if I have a bunch of servers and I have applications that I want to run on these servers, which would be the best server to run, this application instance or this other application instance. And that's pretty much what it does. That's all it does, really. It figures out where to run applications. Now, this entire presentation will be about helping it do that for you in the best way possible. Best way being something that you define, and you can instruct Kubernetes what it actually means. All right, so Kubernetes, the thing that figures out where your software components get to be deployed, it also gets to terminate so-called pods whenever it needs to. Therefore, you almost always need some kind of controller that looks out for your pods. Single, straight-up pods are rarely used outside of, say, one-off debugging. And in fact, now you even have something called ephemeral containers specifically for debugging. So even that isn't a modern use case anymore. There's something called a replica set. If you read the documentation, you don't want to use those either, not directly anyways. So rather, you want to have something called a deployment or a stateful set that will handle pods for you. Now, okay, this applies regardless of whether you intend to run like one instance. Like maybe you only want to run one instance of a component ever. You still want to have something that looks out for that one instance because, as I said, Kubernetes gets to terminate the pod, so you need to have something that would like bring it back up again. So the reason that you want that type of automation is that Kubernetes makes no guarantees about the continued life cycle of a pod in case of a container within it failing. A pod is a collection of related containers. Containers being applications that have been packaged in a nice and neat way. In fact, it's clearly documented that the pod will then just be terminated. Right, so it's the job of some kind of control loop to like get another one going. Okay. Tip number 2, or principle number 2, is that you clearly want to separate stateful from stateless components. Now, that might sound super obvious to you, but this was something that was not obvious before, and also we still see people screw this thing up. So if you have a front end and it like keeps a session or something, that's keeping state in a component that everybody thought was going to be stateless. So, the architect screwed up. Please talk to that architect. This is probably, I'm going to have like a big summary slide at the very end. This is probably the most impactful one, but it's also the most difficult one, ta-da, 5, because that actually means if you don't have this in place, you're going to have to talk to that architect person. Maybe that's difficult. I don't know. So there's a thing called the stateful set, as opposed to a so-called deployment. Now, a stateful set is stable in the sense that it's consistent across pod rescheduling. It's like Kubernetes figuring out new places to put that pod. It has a certain stickiness to it. So once scheduled to a node, you're not really getting rid of that scheduling until you delete the node. If you want to read up on that, there's a GitHub issue. So it doesn't really suffice that the node winds up being unhealthy because Kubernetes goes like, nah, you probably still want it. So you have to actually delete the node. That's not great. Okay, so if you want to run multiple application components or multiple instances of the same application component, you're pretty much forced to use either, but I've seen many convoluted solutions that use the wrong one. So, for instance, for a customer, I was trying to figure out how do I run Microsoft SQL Server in a Kubernetes cluster because, well, I mean, now it can run on Linux, yay. But then all I found was, Microsoft official documentation using deployment rather than stateful set, even though it's a, SQL Server is a very stateful component. And also tons of blogs just repeating that same wisdom. So that was not great. So really just think about, okay, is this component that I'm deploying, is it stateful or stateless? And then just please use the right one. Why? Well, that's the whole point of this presentation. You always want to express whatever it is you need to express about your application in those terms that Kubernetes expects it to. How else would it do the job for you, right? Okay. So, I promised we'd start easy. Okay, so, possibly last rather easy slide, but you wouldn't believe how often I see this being screwed up. Okay, so let's be very honest. There are very few differences on a technical level between the thing that is called a config map and the thing that is called a secret. Both are essentially just key value stores. So they're represented in the same way, roughly, internally in Kubernetes. They're also used in exactly the same way. So anything you can do with a config map, you can do with a secret, vice versa. But using the right one signals your intent. So it also means that they're easier to work with when it comes to role-based access control. Because maybe all developers in your entire organization get to look at non-secret configuration values, but maybe only some of them actually get to read, I don't know, what sort of client API secret you're using in production to communicate with your bank ID integration or something like that. So maybe not everyone gets access to all secrets. Maybe they all get access to configuration, right? So if you're using the appropriate object, so the appropriate resource, namely secret, that's easy to express that, well, here are the trusted developers that get to look at this stuff, here are all the other ones that do not. Whenever I show something related to secrets at all, people always ask, okay, so how do you, I want to store secrets in Git or something. How do I do that? Well, to do that in a secure way, please don't just put them into like a JSON document that you store in Git and everybody can read it. You could use something called sealed secrets by Bitnami, for instance. If later, when you then have these slides, you click that link that says GitOps, you have a very nice, it's not just going to the definition of GitOps, because you can find that on Google very easily. That one is actually a very good article about how to work with secrets that you store in Git, because, well, let's face it, it's very convenient to have Git as a single source of truth, and then you can deploy from Git. It's this whole thing. It's lovely. Right. Maybe if you're really scared of people committing unencrypted secrets. So the thing with sealed secrets is they will be encrypted, stored in an encrypted way in Git, sent encrypted to your Kubernetes cluster. There will be a component in there to like decrypt it and put the information in place in such a way that no human needs to have access to it to actually read it. So that's nice. That's more secure. And then in every single place that it has been stored in an encrypted way. So it's safe. Right. If you're really freaking out about like, oh, we don't want to ever have a secret committed to our Git repo, well, you can use kind of policy as code tool to like forbid secrets from ever winding up stored in Git. So maybe that's a smart thing to do. Right. So that was sort of the first part. That was more about Kubernetes resources. So I only wanted to talk about that. I'm not going to like discuss all kinds of other things. If you have questions, or if you feel like, hey, you forgot this and this and this, I love that type of feedback. But let's just take it afterwards, because a few sessions were running a bit late. Let's not be one of those. So come up to me afterwards. Let's talk. I'll be here all conference. So, if you don't catch me today, you can catch me later as well, some other day. Right. So let's head over to the principles related to automation, because honestly, I think that's probably why you wanted Kubernetes in the first place. I also know that this is where most organizations have the most to learn and to benefit from. So, auto-scaling. Actually, the past of this company that I work for, but we made a predictive autoscaler that, well, predictably nobody wanted. But that was like 10 years ago, 11 years ago. Nobody ever really wants to run out of capacity in their production environment. And similarly, nobody wants end users to suffer because of poor capacity allocation to pods. So preparing for this already from the start means that you will be forced into the mindset that scaling both can and will happen. And this is far more desirable than to run out of capacity. So if you Google for like scalability design principles, you'll find great stuff there. You should already be prepared to run multiple instances of each and every one of your application components. And this is, of course, crucial both for availability, because one thing will eventually fail, and then, you have that single point of failure you're supposed to avoid. So you need to have at least two of everything, so one can fail independently from the other. But it's also key for scalability, because if you already from the start have built in such that you always have multiple copies of each component, that means, well, if today I run 2, then tomorrow I could run 5, and it's probably going to scale pretty well. There's, of course, tools for this in Kubernetes. Something called the horizontal pod autoscaler is available. That can figure out how to scale deployments up and down. So you can set a rule that says if I'm serving this much traffic with 5 pods, maybe I need to scale it up to 7 because, well, that's going to do it. If you heard the control theory related talk earlier, it was highly entertaining, then you kind of want to use this yourself. You can also scale stateful sets with the horizontal pod autoscaler. This is interesting because stateful components, they should typically only be scaled if it's absolutely needed. Because if you're trying to scale, for instance, a database, that could mean that a lot of data needs to be replicated, additional transaction management needs to occur, so like there's more to sync now, and that's definitely not what you want to do necessarily right at the very time that your database is currently being sort of hammered by tons of end user requests. All right, so scaling up before that happens, before it's painful, is of course an idea. So maybe you should do that. If you do auto-scale stateful components, you should probably also consider disabling scaling down in an automated way. I mean, I know I'm saying replace automatic with manual here, but it's probably a good idea to do that, because in particular here, if the stateful component needs like synchronize with other instances of the same component, it could be safer to trigger that manually. So a database that, instead of having sort of active replication, did some kind of sharding across instances. If you just kill one of them, it's not going to be great. So you need to actually inform the others they're supposed to now inherit the data shards that were assigned to the one you're trying to shut down. Yeah, so let's just reiterate that. So scaling up a database right when it's super busy might not be a great idea because it puts extra strain on it. Scaling down, that can also be disruptive to pull off, depending on how data is actually stored. Right, so a container can define a post-start and also a pre-stop hook, both of which can be used to carry out important work to inform other components of the application, of the new existence of an instance, for instance, or that it's about to be terminated. So the pre-stop hook will be called before your application gets terminated, and it has like a configurable time to complete. You can use this to ensure that the soon-to-be terminated instance finishes its work, commits transactions, stores files in a persistent volume, whatever else needs to happen, for an orderly and automated shutdown. Post-start, on the other hand, that's kind of like an init container that, well, doesn't run in a separate container, but in the same container as your application, in that it runs a script as the container starts up. Here, perhaps you could verify that connections to the service you depend on works or something like that. Maybe init container is actually a better choice for that when I think about it. But pre-stop is useful if you want to make sure data gets written to some persistent volume or gets replicated or handed over to some other replica. But you do only have, say, 30 seconds or so to complete all your shutdown stuff. distributed systems, they will fail in more and less intuitive ways than single process systems will. So if anyone loves like monoliths, yeah, they did have a point in the sense that sort of they failed more like as a whole rather than in a piece. The interconnecting network is, of course, the cause of a large class of new causes of failures if you split into microservices. By the way, I still think it's a pretty good idea, but you have to realize you're adding a whole new stuff. You're adding more stuff that can fail between components here. So the better and earlier we can detect failures, the better our opportunities also are to automatically recover from them. To this end, Kubernetes provides us with probing capabilities. All right. So in particular, the readiness probe is highly useful because it signals because if it fails, that's going to signal to Kubernetes that your container, and therefore the pod it's in, is not ready to accept requests. Now, there's a problem, because there's also a probe called the liveness probe. If you're using Kubernetes, you've probably seen the liveness probe and the readiness probe both being used. Problem is, the author of that resource definition probably only meant readiness probe. So liveness probes are often misunderstood because the name is a bit confusing. Liveness in distributed systems means that the component is not like permanently stuck in a state that will require a forceful restart to solve. So think deadlock in a database. You know, like when one part of your code depends on another part of the code, but it then either directly or indirectly depends on the first one. How do you ever solve that? Well, the only way to solve that, in quotes, is to like stop the process and restart it and hope that that situation does not happen again. All right? If that would happen, if it's in that stuck state, then the process is said in distributed systems to not have the liveness property. If it can continue, then everything is just fine. Now, so liveness does not mean that the component is alive in spite of the name. So it can still be sort of doing stuff, but there's something that is stuck and it can't like unstick itself. All right. So it's not about being alive. That's rather what readiness is for. So I'm almost certain that readiness is what you actually wanted to express, because that only expresses that, okay, here's a component that is ready to receive traffic and to deal with it. If it's not, it's just going to be excluded from the list of endpoints that belong to that service, so it's not going to get any more traffic. It's not going to force a restart, so it's going to sit there. It's just going to do whatever. Yeah, it's just going to relax, I guess. It's not going to do anything. It's not going to handle any requests because those are not coming in. So it's only going to wait until it's ready to start serving traffic again. Now, when would that ever happen? Well, I mean, it would happen if here's a component called backend, and here's another and here's a database. If the database is momentarily unavailable, the backend can't store data. Should it receive requests then? Well, I say no, but I know some people say yes, let's talk afterwards. I say no, because I think if it can't actually store data, it probably can't do its job. Now, therefore, that component should not get any traffic to it. It could be because of weirdness in networking that a different replica of the same service actually does have connection to the database and actually can serve data still. So, the component that fails should just say, I'm not ready, and then it won't get any traffic. Is it a good idea to restart that component just because it's not able to receive traffic right now? Well, probably not. I mean, it's not the fault of that component that the database was down, right? And if you restart it, that means you, I don't know, if you're running, say, Java, it needs to like start up again, and that's going to take like a minute. Or if you have data in memory cache, that's going to be all gone because you restarted the component. So it's not very nice of you to restart a component that doesn't actually need to be restarted. It's also slower, of course, because, I mean, if it's just sitting there and it becomes ready, then it's immediately able to serve traffic. So that's probably better. Oh yeah, and there's a third type of probe as well. I need to add that for completeness. It's called the startup probe. It's going to like, as long as the component is starting up, it is now able to signal like, yeah, I'm starting up, so don't do the other probing right now. Just hold those off until I've said that I'm ready, and then go probe this component. This is a pretty tough one. So how many here have used Unix or Linux? Quite a bit. Okay, good. Windows users also have this, but I'm guessing it doesn't have the same exact words. So if you've ever opened a terminal and you've written a command and it's just sitting there and then you hit Control-C, you've used something called a signal, all right? At least in Unix and Linux terms. So you sent a signal. That signal happened to send a signal called sigterm, which tells the process, gently that it's supposed to stop doing whatever it was trying to do. So that process is supposed to have something called a signal handler that captures that signal and realizes that, oh, okay, I need to stop. For whatever reason, I'm told to stop. That's it. If that fails, at least in Linux and Mac, you have a less gentle way of telling a process it needs to stop, and that's by issuing, rather than sig term, which was the nice one, you have sig kill, which just tells the operating system rather that this process is supposed to just disappear, kill it, take it away. Kubernetes uses these ones too. So I'm sure there's something similar in Windows, but Kubernetes uses these ones too. And well-behaved applications should of course respect them, because after they get sent the sig term signal, the application gets about 30 seconds to complete. It's less if there's a pre-stop hook. That means that now would be a very good time to do whatever needs to be done. If there's no pre-stop hook, and it's only the process itself that can do its cleanup, now would be the excellent time to do so, because now is when you have the time. Because after the grace period is over, sig kill comes in. All right. Perhaps not very surprising. I mean, it's great that you now know a bit more about like how components or like how pods are being shut down in Kubernetes. You know how to start them. Now you also know what happens when they're supposed to be terminated. Now, the problem is you need to explicitly provide a sig term handler. As I said, you need to do something smart when that signal comes in. Otherwise, it's just, you're not going to react to it. You must add to your application code a function that gets called when this signal arrives. And here's where it gets even worse. Because the fact that your application, I mean, if you're writing in Python, for instance, many people here are probably Python programmers. The fact that you write something in, say, Python, and then you try this in your terminal, in your computer, and you can do the Control-C thing, like I said before, so it's going to stop then. That's great. You didn't even need to write a signal handler. Awesome. Python is great. The problem is, well, okay, it gets more complicated. So the main process in your container is called the entry point of that container. All right? So that is the thing that will get signals from the Kubernetes kubelet, the thing in Kubernetes, like on all the worker nodes, the thing that actually starts containers. That's going to get, so your entry point is going to get that signal. Now, if you are a Linux user, which it looked like roughly half are, you are familiar with what's called an init system. So the first process that starts in a computer, right? The one that starts all the other processes, sort of the thing that boots up the computer, essentially. Right after the kernel has started, then there's an init system that owns all the other processes, right? Technically speaking, your entry point, so the main program in your container, is an init system. And that means it can't have a default signal handler. It can have a default signal handler when it's running as a normal process, but as soon as Linux runs it as an init system, that's gone. It doesn't have a default signal handler anymore. That would be kind of weird, actually, if you could just hit Control-C or like send a sig term signal to the entire init system. Your entire operating system just goes poof, right? So it would probably not be a great idea if it had a default one. So that's why it needs to be provided. And in the case of your application, it needs to be you that write it. It gets even more weird. I'm not going to talk about what a zombie process is, but technically it's also responsible for dealing with that. And there are weird things that will happen if you don't deal with it correctly. By show of hands, how many actively know that they are dealing correctly with zombie processes in their Kubernetes application? One person. Okay. I love you. Everybody else, maybe this is what you learned. I don't know. Right, so observability, right? I think it's highly important that we deal correctly with observability. And what do I mean by observability? I know it's a bit of an overloaded term. Well, I think it's something that basically rests on the 3 pillars of monitoring, logging, and tracing. So simply making just custom metrics available to your monitoring system, say Prometheus. If you write structured logs, just output stuff in JSON format, and something smart will come pick them up and separate into fields and values. And as long as you don't purposefully throw away HTTP headers, because you can put correlation IDs in there, that's going to and making the headers also part of what you log, that's going to provide your application with all it needs really to be highly observable. That means that you can trace every log line related to handling a specific request, no matter where it came in, or it's going to come in through your API gateway or something, but throughout your entire system, as long as you just keep that correlation ID, your request ID there, you'll be able to figure out exactly which operations happen and which components related to that one request. So that's great. It's like poor man's tracing. If you want even more detailed tracing information, you can integrate with, OpenTelemetry API or something like that. That's going to make your application even more observable, because then you can actually draw some kind of waterfall-ish graph that says, this component called this other component. Here are the timings it took. Here are the operations that were invoked. All that good stuff. It also makes it easier if you have some kind of custom metric related to your application, like say, length of stuff in the work queue, or the amount of users that are currently logged in, or how many transactions you're currently running, or whatever, to auto-scale based on something that makes more sense than just here's my CPU usage and it's 80%. Google wrote a book about site reliability engineering. They have this great thing about the 4 golden signals: latency, traffic errors, and saturation. If you track these with application-specific metrics instead of just CPU usage or whatever, in my experience, that is going to provide you with tons of more insights and better ability to actually deal with stuff as it comes up. I'm going to wait a short while because somebody wants to take a picture. Yeah. All right, no. You can set pod resource requests and limits. And if you do so appropriately, that means the horizontal pod autoscaler knows exactly how much resources one instance actually requires. That means it's also going to be better at scaling up appropriately rather than just having to guess. Also the cluster autoscaler, because actually a Kubernetes cluster can grow and shrink. I would really advise you to not set them too low. It might be tempting at first to set them lower than what you think, because it allows the cluster to run more pods essentially. And if you have people talking about budgets, breathing down your neck, and they're saying, you need to reduce the size of your Kubernetes cluster, just stuff more into them. Yeah, then you can reduce the number of resources you request as a pod starts up. Now the problem is, of course, that if you wind up with a very densely packed cluster and and you have tons of users that actually want to use your system, you're scaling up, you're filling it, all of a sudden, all those pods that maybe requested something low, in practice got a bit more resources, but not above the limit, they're now being squashed down to the level that the minimum level that they requested, and all of a sudden you scaled up, but you actually got crappier performance. Now that's of course not what you wanted to do, but ironically, it's what you told the scheduler to do. So don't tell the scheduler the wrong thing. Tell it however much resources you actually need, and let the people with the wallet just deal with it. All right, so that's like capacity management. So on the topic of capacity management, you have like namespace resource quotas. You can reserve compute resources on your nodes. You can set pod priorities appropriately. All that helps ensure that the cluster that you have has enough capacity and stability isn't compromised. So that's really good. Now I've personally seen, I've been responsible for when this happened. This was in the early days of Kubernetes, many years ago. A cluster become overburdened to the point where even the networking plugins pods were not starting correctly. And that was a really fun issue to troubleshoot, because pods came up, but they didn't have IP addresses on those particular nodes where the plugin was not running. It was horrible, but interesting anyways. So please make sure to reserve capacity if you need reserved capacity. You have the tools to do so, use them. If for whatever reason you need to spread out or consolidate pods, say spreading out for redundancy purposes, because you don't want to have a database and a replica and its second replica all running on like the same server, because if the server needs to be rebooted, your entire database cluster went down. Oops. So there's a case for spreading them out. Or if you have stuff that communicates all the time, say something that you install the cache specifically so that it wouldn't hit the database all the time, maybe you want to co-locate that very talking component with its cache. You can express these things using so-called pod topology spread constraints, as well as something called affinity and anti-affinity. So you really should do that. You should also spread across multiple cloud availability zones if you have those. There are things called disruptions in the Kubernetes world. So you can disrupt a pod by shutting down the node where it's deployed, or by deleting it, or by issuing a rolling upgrade. Those are voluntary disruptions. Involuntary ones are, when just the virtual machine fails or something. Voluntary ones, they are controlled via the API, and there's something called a pod disruption budget, where you can say, at most, one out of these 3 pods gets to be voluntarily disrupted at a time, because I really care about this cluster being up and having sufficiently many members in it so that it has like quorum and it can do its job. You can use this. You can use it in an inappropriate way as well. The math works out such, because you can set this in percentages and then forget that you did, and then really screw stuff up. I don't really have time to go into it, but yeah, I've seen horrible things where people made system maintenance impossible by setting pod disruption budgets on databases and then just forgot about it. This like under construction GIF, or how your bank probably has like this, oh, we have maintenance between this and this time, sorry, service not available. That's not really going to fly unless it's a bank and their customers are locked in anyways. So you really can't just stop the world. You need to do something smarter. You need to have a nice deployment strategy, such as partially replacing a deployment, or side deploying new version and old version, and then just load balancer switch from one to the other, so that you can easily deploy new versions with 0 downtime, because it's not acceptable anymore to have downtime because you're just upgrading stuff, especially not if you want to release multiple times a day. That would just be annoying. So you can implement this. It's rather difficult, but there are tools out there that make it easy to do. The difficult part of it is not really network traffic stuff. It's more architecting so that you can do this. All right? How do I make sure that the old version and the new version can both run at the same time without, the whole system getting all screwed up? Let's talk about that stuff afterwards as well. Second to final thing, Kubernetes is not safe by itself, nor by default. You can configure it to enforce some kind of security best practices, of course, such as limiting what the container can do on the node. Don't run as root. If you think you do, well, no, you don't. And if you really actually need to run as root for some reason, probably not all permissions as root are needed, so you can drop what's in Linux called capabilities and then just add the parts back that you actually did need, like, say, something related to networking or whatever. Maybe you need that, but then you don't need to have all kinds of nice file system access. There's also a problem in that in Kubernetes, by default, pods get to automate stuff in Kubernetes. That's great, but if your pod is not actually supposed to automate stuff in Kubernetes, not actually access the Kubernetes API, why in God's name does it actually have permission to do so? Well, by default it does. So you should stop that. That's a setting. You can disable it. And of course you should. There's also something called pod security standards these days. It used to be called something else. You can have those like prepackaged settings to make sure you limit what can happen in your Kubernetes cluster. Use network policies the same ways as you use a firewall, because obviously you're going to use a firewall. And yeah, just lock that stuff down, because it's not actually supposed to automate things in your Kubernetes cluster. Also, it's not supposed to automate things with your cloud provider's metadata service either, but many people leave that one open as well. I hope we have some nice security talks where people just show all the kind of fun things you can do. Right, so those were the 15 principles. Here they are again, 16 principles, sorry. Some people want to know what would be the most impactful to implement. I think probably the probes. So that, and to make sure you have correct resource requests and limits in place so that you have everything you need to enable reasonable scaling, right? So unless you have probes, how would you know if a component works or not? So don't scale unless you can figure that out. And unless you have resource requests and limits, how is the scaler supposed to know how big to scale? Oh yeah, and if you have a very nice architect, you know, the most impactful thing overall is of course to separate stateless from stateful. This talk is based on an article. You can find it online. Please go to the site, read if you found this talk interesting. I know it was kind of like speeding up a bit. And if you have a question, I don't know if we had time for questions, but if you do, then please fire away, or come find me, or find me virtually on LinkedIn. Let's have a chat. All right, thank you.